It works? Does it work? Okay. Thank you very much. First, I thank Gerhard for organizing such a comfortable conference. We all enjoy this conference. Then, main topic of my talk is about an uncertainty relation for error disturbance. Yeah? We have just now had a theoretical reconsideration and reformulation of Heisenberg's uncertainty principle. Then I'm going to explain the first experimental demonstration and verification of uncertainty relation for error disturbances. Yeah? Then I'm doing the experiment with neutrons. Then before I go into more detail, I'm gonna give a short introduction for neutron optical experiments. Namely, we are using a neutron interferometers and polarimeters. And in neutron interferometer, yesterday, Helmut has explained the neutron interferometer. He has also started exactly the same slide here. We are using neutron. Neutron have particle properties, just like a mass, spin, and magnetic moment. Yeah? On the other hand, neutrons have a wave properties. Just we can see the interference. They have the de waves. Then typical wavelengths are 2 angstrom and 2 kilometer per second, and 20 millielectron is the kinetic energy. Yeah? This is our neutrons. The neutron have the de wavelengths. Then they follow the Schrödinger equations. Then, okay, neutron have a wave and particle properties, and it is very important. They follow the Schrödinger equations. Then I should mention that there are many experiments with photons. Namely, some experiment has been done with laser beam. Yeah? Then they claim that this is a new quantum phenomena and so on and so on. But it seems to me quite strange. Yeah? If one can do the experiment and the experimental results with a laser and a single photon source, if they are exactly the same, what are they demonstrating? It is really a quantum phenomena, or it is purely classical phenomena. Yeah? I'm always wondering this question. Then, but with doing the experiment with neutron, there's no such a question. Neutron is a quantum object. There's no Maxwell equation. We are using only Schrödinger equations. Yeah? Then our phenomena with neutrons, demonstrated with a neutron, is only evidence of Schrödinger equations. Yeah? It's quite simple. Yeah? Then also, today's main topic is about uncertainty relation. Heisenberg has proposed in 1927, delta x times delta p is larger than h. At first, he said roughly the h. Afterwards, our modern constellation is h over 4 pi, or h by half. Yeah? Then, okay, let me explain a little bit about the neutron interferometer. Yeah? And yesterday, Helmut already showed the neutron interferometer. We are using a single perfect crystal interferometers. Then split beam, incident beam go into 2 split beam paths. Then there's a beam path 1 and beam path 2. Then they are recombined. Yeah? Now, this beam separation is typically 5 centimeter, 2 centimeter to 5 centimeter. It is really macroscopically separated beam. They are recombined. They show that interference fringes. Yeah? Then we can also insert a phase object sample in one of the beam, or we can manipulate the relative phase with a phase shifter. We can tune quite precisely the relative phase between these 2 beams. Yeah? Then in the neutron business, your neutron is an up, down, down quark composite structure, but neutron have also a definite mass, 10 to minus 27 kilogram. It's very, very small mass, but it is definite mass. Then spins, okay, spin we are going to use in the polarization experiment. Yeah? Also magnetic moment, and the lifetime is roughly 15 minutes. Yeah? Then, okay, we are using interferometers. This is pictures of the interferometers. In the 70s, when the Helmut have invented the interferometer was quite small. Yeah? But nowadays, we can have such a big interferometers. Beam separation is 5 centimeters, and beam, this propagation length is up to 20 centimeters. Yeah? It is, I again emphasize, neutron interferometer experiment is a quantum experiment in a macroscopic scale. Yeah? So then with this kind of interferometer, we have also done some entanglement business. Yeah? Then Bayes inequality and entanglement, bipartite entanglement, Normally one assume the two-partite entanglement, two-particle entanglement. Yeah? There's a single stellar source, there's a one particle go to the left side, the other particle go to the right side, then there's a correlation is measured. Yeah? For neutrons, such a source to emit these kind of entangled pair, it is, yeah, there is such a source, but intensity is very, very low. Yeah? Then maybe if we want to make a Bell's inequality experiment with two pairs of neutrons, yeah, one should wait several years, 10 years, 20 years. Yeah? It takes a little bit time. Yeah? I'm not so patient enough. Then I find another strategy. Our strategy is to use the degrees of freedom of neutrons and make these degrees of freedom of neutrons entangled. Namely, in the first experiment, we have made an entanglement between the spin degrees of freedom of neutrons and path degrees of freedom in the interferometers. Yeah? Then, in this case, beam path, there's a beam path 1 and beam path 2. It's a two-level quantum system. Then, in the beam path 1, there's a spin is up. Then, in the beam path 2, the spin is down. Yeah? Then, there's two kinds of observable spin observables and path observables. They are represented exactly by the Pauli matrices. Yeah? Then we have measured a correlation of the spin part and the path part. Then we have analyzed by Bell's inequality. Then, yeah, it's 10 years ago, we have showed the first violation of Bell's inequality using degrees of freedom of single neutrons. Then afterwards, we have done some experiment concerning the Kochen-Specker experiment. Kochen-Specker experiment means we can show the contradiction. In the Bell's inequality, the statistical violation from the 4 expectation value or the correlation expectation value. In the Kochen-Specker experiment, in principle, we can show the contradiction between from the naive hidden variable theory, or in our case, it's a contextual theories, between the contextual theory and the quantum predictions. Yeah. Then also we have done some this three-partite entanglement system. Then first experiment was we have used a GHZ, Greenberger, Horn, Zeilinger state. It is an 000 plus 111 states that we have analyzed using the Marmin inequalities. Then quite recently, 2013, we have also generated a so-called W state. W state is 1, 0, 0, 0, 1, 0, 0, 0, 0, 1 states. Yeah? It's a three-partite entangled states with 3 terms. Yeah? Now also we have used a GHZ state, and we have used an entanglement witness. Then we have analyzed this multi-partite entanglement in the neutron system. Then, okay, quite recently, we have done also a different kind of experiment concern using weak values. Namely, some of you have heard of the Cheshire cat. Yeah, Cheshire cat is a cat in the Alice's Wonderland. Alice have seen the cat. Afterwards, cat disappears, but there isn't smiles. Yeah? Then this is the situation for the quantum Cheshire cat, right? Then in the double slit situations, there's an incident beam, there's an outgoing beam. Then in between, cat is on one of the beam paths, but smile is on the other beam path. Yeah? Then in the neutron case, if we use a neutron or electrons, yeah, cat is a neutron. Yeah? Neutron is here, upper beam path, but neutron spin is in the lower beam path. Yeah? Neutron is in the one of the beam, but there's no spin here, but the spin is on the other way. Yeah? Then I'm gonna explain only qualitatively, yeah? But quantitatively, one can explain this situation with weak values here. Yeah? Then in the neutron experiment, we have made a polarized neutron beam here, then here's the interferometers, then there's beams, there's spin manipulations here, then phase shift afterwards. Yeah? Then first, neutron part, yeah, where is a neutron in the interferometers? Yeah? Then we have put an absorber here in lower beam path. Okay? We put an absorber with a transmittivity 1.8.6. and rotating a phase shifter here. Yeah? Then in this case, there's no interference fringes, and with an absorber, with a strong absorber, there's no change. Okay, because neutron is not here. Yeah? Let me see if the neutron is on the other path. These are next situations. If we put the absorber here, exactly 1, 0.8, 0.6, then rotating a phase shifter, okay, there's no interference fringes, but you see, yeah, intensity reduces. Oh, neutron is here. Yeah? Oh, no, here is an absorber, yeah? Then if I put the absorber, the intensity changes. It means, okay, neutron is here. Neutron is upper beam path, but neutron is not in the lower beam path, okay? This is the situation exactly here. Okay, this is a cat, in between, cat is here. Yeah? How about the spins? Okay, in this case, first spin is prepared to right and left. This red. Then we're gonna rotate and spin on the upper beam path, and we're gonna rotate the spin on in the lower beam path. Let me see what happens. Yeah? Then first, we have seen that if this spin rotation is exactly, precisely carried out. Okay? In this situation, it is so-called the H beam, is one of the beam without a spin analysis. Then we will see this orthogonal spin state, there's no interference fringes. But if I rotate on this lower beam path, and the spin of the lower beam path, we can obtain these oscillations. If I rotate the spin on the upper beam path, we obtain these oscillations. Okay, spin is rotated. Yeah? But the point is, if one makes a spin analysis afterwards, it means it's in a post-selection of the neutrons. Yeah? In this case, first one is no oscillations. Yeah? But if one rotates and spin in this beam, yeah, then oscillation, yeah, this is only the fit. Yeah? Then it is a very small fit. Practically, there's almost in the fluctuation. Yeah? But there's a fit, this oscillation is very small. But in this, if you want to rotate the spin in this lower beam path, there appears big oscillations. It means here, spin is lower beam path, okay? Then in the first experiment, we have shown that the spin, neutron is the upper beam path, but in this situation, we can say spin is lower beam path. Or neutron is the upper beam path, but spin is lower beam path. They are separated, yeah? This is a Cheshire cat experiment. Quite recently we have done. Yeah? Then also, another strategy of the neutron experiment which we are using is neutron polarimeter. Polarimeter is an instrument to measure the spin of neutrons. Then normally there is a part to make a neutron beam polarized, and there's a part of the analyzing spins. The in between, we can manipulate the spin from up to right, left, up to down, and so on and so on. Then in this instrument, it is important thing is that we have a plus-set spin. Yeah? This is an X, Y, Z axis and plus-set spin. But quantum mechanically, this plus-set spin is a superposition of plus Y and minus Y spin states. Okay? It means if one have the up spin here, plus Z spins, this is exactly the superposition of plus X, plus Y, and minus Y. Then we can observe more or less this phase shift between the plus and minus Y spin states in this spin analysis system. Then, what is a big advantage? What is an advantage of the polarimeter experiments? Yeah? Polarimeter experiment, you can see here, the contrast is quite high. Yeah? In the interferometer experiment, we can obtain 91%, 92%. Then normally we can do the experiment at 80%. Yeah? But with a polarimeter experiment, you will see here, 98.5% contrast. It is exactly maximum to minimum. Yeah, this oscillation, sinusoidal oscillation, minimum is very, very small. We can obtain up to 98.5, 99% contrast. It is a big advantage of the polarimeter experiment. And with using this kind of instrument, we have shown the non-commutability of the power matrix or the Bell test, or alternative model by the Leggett. It's a contextual model of the quantum mechanics, or GHS states, entangled state was also analyzed in these instruments. Then I'm not going into more detail, but we have quite recently have done the have observed a spin rotation coupling effect in the quantum mechanics. Then I emphasize this spin rotation coupling this effect is really a relativistic effect appearing in the quantum mechanical regime. But I'm not going to explain in more detail this experiment. I only mentioned this is one example of the high contrast. This is the GH state was used, and this is the Marmin's inequality business. Yeah? Then in this case, this sum of some expectation values, theoretically it is predicted that M is 4. Then experimentally we have obtained the M value is 3.936. Yeah, loss is only 0.064. Yeah? It means contrast is really, really high, 98.5%. It is really a good advantage for some experiments. Okay, good. It was an introduction of the neutron optical business. Then I'm going to explain the first experimental demonstration and the confirmation of the uncertain relations. Yeah? You have heard this theoretical background of the Heisenberg's and the new uncertain relation by Ozawa. Then, yeah, some of you speak in German, so this is the original, yeah, from the Heisenberg's paper. He said, this is der mittlere Fehler. It's a mean error. Yeah? Der mittlere Fehler, the mean error is one part, is a Q1, and another one is this die unsättige Änderung, and continuous change. Yeah? This is the original word of the Heisenberg. Yeah? He said mean error times this continuous change is roughly h. Yeah? This is the first argument. Then, okay, this is nearly equal or there are some factors. In the modern terminology, we can say it's an error of the measurement and times the disturbance of the measurement have a lower bound given by the h bar half. Yeah? This is quite, before the Ozawa's derivation, everybody believes, maybe, I think, yeah? All of you, or also I believe this is correct, yeah? But he showed this is wrong. Yeah? What happened? Yeah? Then, of course, there's another argument of the uncertain relation using this standard deviation. It's a distribution of the wave packets, wave function, more or less. Yeah? This is explained by this sigma. It's a standard deviation of the results of one measurement of the one observable. Yeah? Then, in this case, this is sigma position times sigma momentum is larger than h bar half. Yeah? It is okay. It is correct. Yeah? It is mathematically proved. Then, yeah, more or less in a single slit situation, it is already shown. Yeah? But our question is here: this error of the A measurement times the disturbance of the B measurement is larger than this border. Is it really valid? It is true? The answer is no. Then Ozawa it is already 10 years ago, yeah? It's amazing, yeah? 10 years ago, Ozawa sensei have already derived these universally valid uncertain relations, yeah? Let me see if it is correct, yeah? Then he also suggests an experimental method to derive error and disturbances. Then now we can say it, and in this method, we should measure the 1, 2, 3, 4, 5 terms. Then it is this is the psi is incident states. Then A psi is psi times operator A. Yeah? Then this is A plus I psi, and psi in incident state is operated by A plus I operators. Yeah? Then some say it is a three state method, or I'm going to say it's a topological method. Yeah? It is have something to do with this process tomography in quantum information business. Yeah? Then, okay, our scheme is to use neutrons to make a spin measurement instead of the position and the momentum. Yeah, position and the momentum measurement, it is hard to make such a really, really precise measurement. Okay, let me show first the uncertain relation in the spin measurements. Okay, this is a scheme. We prepare the spin in the instant state. It's a polarized spin state. They make two measurements, one after another. Okay? The first measurement there's a meter, then we can see the first results of the first measurement, followed by second measurement. Then in our experiment, tactics is we have detuned the observable of the first measurements. Yeah? Then in practice, in practice, we have prepared and plus Z states. Then we're going to measure the X states followed by the Y states, Y measurements. Yeah? Then here is A is a sigma X, here is a sigma X, here is a sigma Y. What we have detuned from X to Y, we have detuned the observable, which was realized in the experiment. This is an observable in the experiment. This is an observable to be. Yeah? Then this detuning makes errors, and depending on this observable, there's an error on the second measurements. This is our tactics. Yeah? Okay, then there's a theories. We prepared plus Z incident beam. Then each first measurement should be X direction, followed by the Y direction. Yeah? But first experiment, we have detuned this X measurement, the direction of the X measurement in this plane. Okay? Then this is theoretical predictions. Theoretically, yeah, this is the error of the A measurement or the X measurement. If I measure the X direction, of course, we want to measure the X, and if we measure the X, there's no error here. Yeah? But depending on this angle between the measurement and vectors, there's this error getting larger and larger. Then on the opposite side, there's a big errors. Yeah? Large error is very, very large. And also disturbances. Disturbance depends on the first measurements. Yeah? Namely, if the first measurement is X direction, what it should be, yeah? This X direction, the error disturbance is very, very big. Yeah? Okay, X measurement followed by Y measurement. Yeah? This X measurement completely destroyed the information, maybe information of the Y direction. Yeah? That's why into this X region, this is a disturbance very, very large. But let me think. If I measure the Y direction first, followed by the Y measurements, in this case, there's no disturbances. Yeah? Say here, in this region, if I measure the Y direction first and followed by the Y measurement, disturbance is very, very small. Yeah? This is a theoretical prediction. Good. Then this is a Heisenberg's relation. In this region, this is a border of the Heisenberg's uncertainty relation. In this region, this Heisenberg's product is smaller than the border. Then new uncertainty relation derived by the Ozawa is always larger than the border. Okay, let me see if it works. This is the experimental setup. This is a blue region is a preparation of the spin. It's an up spin, is prepared. Then we need some additional spin state. It's in the X state or the Y state or the minus Z state. Yeah? We can prepare it here. Then followed by the X measurement, A measurement, but there's a slight detuning in practice. Yeah? Followed by the B measurement, it is a direction to Y. Okay, let me see. Okay, this is a picture. Here is a reactor. Reactor is in Vienna. If you have time, you can come to our Atomic Institute on Monday. Yeah? I can show the reactor, also the setup. Yeah? So this is we have used a reactor in Vienna. Then here is a reactor. Then here is a monochromator inside, and here is a polarizer. Here is a first manipulation part, and the second analyzers. Yeah? Followed by here is also second step manipulation, and here is a second analyzer, followed by the detector. Okay? Then in this experiment, we send 1, 2, 3, 4 states, then measure some expectation value. Then in this case, it is output is always up or down. It means a +1 or the -1, or plus, minus, minus, plus. And these 4 is a one pair to determine the expectation value. Yeah? Now from these data, we have calculated each expectation value, then we can derive or obtain this error of the measurements. Yeah? Then this is a parameter of the detuning. If one measures exactly the X direction, this is corresponds to X, error is very small. Yeah? But if detuning is getting larger and larger, then the error is getting larger and larger. Then on the other side, if we measure the y direction, then disturbance is very small. But if this detuning is from the y direction, if there is a detuning, then disturbance getting large. This is a really a trade-off relation between the error and disturbances. Then, okay, let me see how the Heisenberg's product is an error times disturbance, and how this sum of the derived by the Ozawa looks like. In this case, you see, here's a border. Here's an uncertainty principle, uncertainty relation border. Then in this region, this error times disturbance is always below the low border. And you will see here is really near to the 0. Yeah? And then on the other hand, the Ozawa's sum is always above the border. Oh, great. Yeah, Heisenberg's product, Heisenberg's uncertainty relation is violated. The new relation satisfied on this experimental data. Yeah? Then after our publications, yeah, as Ozawa said, there's another experiment appeared. Yeah? From Canada, they have measured spin, not a spin, it's a polarization of photons with using this weak measurement scheme. Yeah? Then they obtain, this is a Ozawa sum, this is a Heisenberg sum. Yeah? Then, okay, I only mentioned, this is roughly the same, physical, it's the same parameters. Yeah? Then we obtain this orange line, this corresponds to this one, then this red line is a broken line is here. Yeah? Okay, our scheme, I should say, our scheme is an error of the measurement is quite small, and we can obtain really up to near to 0. Yeah? But okay, another scheme works. Yeah? It is then another scheme shows also then this relation, these two relations. Heisenberg's relation is wrong, then Ozawa's relation is correct. Yeah? Then also there appears also another experiment from Australia. Yeah? Then another theoretical improvement appears also in Australia. Then from Japan, there's also another experiment. Oh, it's great. Yeah? Then, okay, now we have also extended our analysis for large regions. First region is only here, yeah? Only this region. Then Ozawa's sum is here, and we have extended some parameter region. Then in this case, there's both relation satisfies inequality, or this is also asymmetry appears. Then also in this case, this is also important. Yeah? We have obtained the case when this point, or the obtained measurement point touch the border. In this case, this is within the almost touch the border, and in this case, this data really touch the border. Yeah? Good. So I'm gonna give a conclusion. Neutron interferometer experiments, namely the interferometer and the neutron interferometer polarimeter, are very powerful tool for the investigation of quantum mechanical phenomena. Then, in this case, the universally valid uncertainty relation by Ozawa is experimentally tested. Then neutron spin measurement confirmed the new error disturbance uncertainty relation. Then new sum is always above the limit. Then Heisenberg's product is often below the limit. Then, yeah, this is an Atomic Institute. If you have no time on Monday, you can come. It is welcome. We welcome you to come to the institute. And these are our colleagues who are involved in the neutron business. Thank you very much. Yeah.
Okay. Yeah, I'm very intrigued by your results and previous talk, but on the other hand, I have the feeling that quantum mechanics will not change. We know the whole Hilbert structure and all the way to do it, and I would not believe that anything changes. So what is...
Quantum formalism doesn't change. Yeah? We are using Schrödinger equation. It's clear. Yeah? But our old belief, Heisenberg uncertainty relation, it's not correct. Yeah?
So the deeper interpretation of what is going on has to be...
Also, I should emphasize that his work by the Ozawa, he's really treated on this measurement process, measurement and procedures mathematically, then it is really testable by the experiments. It was not the case 8 years ago. Heisenberg's original paper, he only qualitatively show it's an uncertainty relation. But now he made a correct, precise this treatment, and we can show the experiment. I think it's great.
So deeper understanding.
So, do you know the Nevichevsky experiments on which neutrons are bound? Would you expect that you could do the same type of experiments there?
No, I don't get your point. What is it?
You see, Nevichevsky and collaborators have produced the bound states of neutrons in a reactor. And so it's a completely different setup. But,
it's completely different,
Yeah, but quantum mechanics should hold as well, and there are uncertainties and so on and so on. So, I mean, there should be some complementarity between the two things.
We are using a thermal neutron, 2 angstrom wavelengths and 28 milli electron volt kinetic energy. It is very suitable for crystal experiments.
Okay.
Is a locality loophole present in your tests of?
No. Locality have nothing to do with our experiment. We are testing contextualities instead of locality. Quantum contextuality is there's two observers which are not commuting. These observers are involved.
Actually, I'm not sure. So. Are your tests of Bell inequalities violations loophole free?
Loophole free. Ooh. Yeah, in some sense, but there's also some laws in the interferometer. Then I cannot really exactly argue on this point. Okay. But argument is not a locality, non-locality. It's a contextuality, non-contextuality. It is completely different physical quantities.
Thank you.
Excuse me, this change in uncertainty principle, does it also apply any change in Heisenberg algebra or non-commutative relation we are using in general in all fields of quantum mechanics, or you think it just shows that there is difference, there is not direct relation between uncertainty, which we are seeing in the term of experiment, and Heisenberg algebra?
Well, I mean, algebra itself is, I think, the same. It is algebra, quantum algebra. We are using a quantum algebra. But the results or the prediction is completely different.
I mean that this specific type of non-commutative relation that we are using will change with this discovery or not?
By what effect?
The relation between X and Y in Heisenberg algebra, the non-commutative relation will change or will stay as it was?
No, I don't know what you mean. No, algebra have nothing to do with, algebra is exactly the same.
Quantum mechanics with this. Oh.
You can change the
I would like to ask, it seems to me that you disproved the single event Heisenberg uncertainty relations, which were originally done by Heisenberg. But what about the derivation which is based on statistical argument by Schrödinger and...
statistical argument, you mean that it's a standard deviation?
Yeah, in standard deviation language, that's not violated by your experiment.
No, it is correct.
Because it's mathematical identity, so it should be hardly violated.
Yeah. But in a statistical, this standard deviation, we make a repeat measurement, then we get the statistics, right? It is completely different properties. Can you Heisenberg mentioned.
So can you basically say that the single particle interpretation of quantum mechanics is violated by non-statistical, let's say, ensemble interpretation of quantum mechanics?
No, I mean that in a big, how do you say, that also have derived different quantities. What is error? What is a disturbance? What is a standard deviation? These three properties are completely different. Then we cannot mix these three properties.
Because Heisenberg in his original paper, he was not very specific how to define, for example, uncertainty. It was dependent on the experiment. So
error of the position and disturbance on the momentum.
Thank you.
I think this was more just a comment about maybe an answer to your question, that I think, yeah, clearly there's no change in the algebra, and I think the point of the question is, the point of the experiments in the uncertainty relation is that what is different is that the Heisenberg uncertainty relation, in the sense of multiplications of standard deviations, does not apply to measurement accuracies and disturbances.
Yeah, correct, yeah.